Okay, so it's 12 o'clock. It's my great pleasure to introduce Charlie Steinhorn from Vassar College. And also, for many of us, we should give him a big thanks as for a longtime treasurer of ASL, keeping the ship afloat. Many thanks for that. So today he's going to talk about asymptotic and multidimensional asymptotic classes in finite structures.
Okay, thank you, Chris, and thank you to everyone for the invitation, and thank you to all for sitting through yet another Zoom talk. So I know that there are at least a few who popped up who are non-logicians, so at least I will make every effort to make this accessible, at least in bits, to non-logicians. So I'll start by whoops, the screen is not advancing. There we go. So this is a lot of this long-term project is joint with Dougal McPherson. And then when I say et al, there are people who have worked with Dougal and me, and there are people who have worked independently, and I'll make all of that clear as we move along. So the outline of the talk is I'll start with some motivation. Then I'll discuss asymptotic classes, and then I will discuss multidimensional asymptotic classes. So starting with the motivation, what I'll say is the point of view that we have for this project differs from that which is usually associated with the term finite model theory, which lives at the intersection of theoretical computer science primarily and logic. And which is has a long history with a lot of impressive work. Ours is just a different viewpoint from that. One aspect of this work has been looking at classical model theory in the finite context, but much of that really just breaks down when you restrict to classes of finite structures. I feel, though, that I should mention a beautiful exception to this, by Ben Rossman in 2008, which is the homomorphism preservation theorem is valid when restricted to finite structures, saying that the formulas that are preserved are the existential positive ones. But this is just to note that something does happen there, but still very different from what we're going to be doing. So the inspiration for this work has its origins in contemporary infinite model theoretic themes such as independence and dimension and various measures of the complexity of definable sets. And I think we're seeing this, this work being done by lots of others. For example, in Gabe Conant's beautiful talk yesterday, and work of Caroline Terry, with Anand Pillay, work of Marianthi Maliaris with Saharon Shelah, and work of Artyom Chernikov and Sergei Starchenko, just to name a few, I think are very much doing work in this spirit. And I'll say that there are connections to infinite model theory that I'll point out along the way. So where does our work start? Well, it starts with the following beautiful theorem of Zoe Chatsidakis, Lou Van den Dries, and Angus McIntyre. So let phi be a formula in the language of rings. The language of rings is just where you have addition, multiplication, minus, and the constants 0 and 1. And so what's basically being done here is counting solutions to these formulas, just like counting solutions to equations. And this is going to be over finite fields. So let this phi of x1 through xn, y1 through yn be a formula in the language of rings. And then the point is that basically there are finitely many pairs di mu I, with the d's from 0 to n, the number of x variables, which we'll call the dimensions, and mu's, which are positive rational numbers, which we'll call their measure, such that for each finite field and each set of parameters, which you can think of, for those of you who are not logicians, just think of parameters as being coefficients of polynomials, for example. So these are the y variables here that we're putting in. Then it says that if the set of solutions, so the set of n tuples in FQ satisfying this formula phi is non-empty, then there is an I less than or equal to k. So one of our finitely many dimension measure pairs such that the number of solutions to the equation basically looks like a fraction mu I times q, which is the number of elements in FQ to the di'th power. So the di, so you have a dimension q to the di and some fraction of that. And just read this as saying that the number of solutions is approximately equal to mu I q to the di. The reason why you need rational numbers for the mu's is, for example, if you think of the formula that says that an element is a square, you get basically that 1/2 of the elements of FQ are squares. So the size of that set would be roughly on the order of 1/2 Q. So that's the first part of this. Then there's a second part that plays a very important role in what comes, which is the definability of dimension and measure. So what it says is that for each dimension measure pair, which is giving you the size of these sets, there is a formula such that for all finite fields, the set of m tuples, the set of parameters for which di mu I is the relevant dimension measure pair, is definable. So this is definability of dimension and measure. And this theorem is based on the, uses the Langevin estimates combined with a partial quantifier elimination. And it's the fact that you have quantifiers, as I indicated in the case of squares, that requires the rational coefficients here. So this theorem was turned into a definition by Dougald and myself of a one-dimensional asymptotic class of finite structures. So what you want to do is just think of this as a formula in some language, and you're dealing with some class of structures, and you're saying that you have this same uniformity for the number of solutions. So for each formula, there are these finitely many dimension measure pairs such that in any of the structures in our collection of finite structures, the solutions look like one of these finitely many mu I q to the di, roughly speaking. And then I'll go on from here to talk about, so in what follows, we'll just let L be a first order language and C a collection of finite L structures. And so a definition, which I'm not sure I like the name of this anymore, but turning around names after 10 years is like trying to turn around the Titanic. So we'll say that a collection of finite structures is an n-dimensional asymptotic class if for every formula, just as before, you have the parameter variables, think of these as coefficients, and the variables that are free, whose solutions you're trying to count, there are the finitely many pairs di mu I, but now the d's can range from 0 up to little n, the number of variables, times capital N, the dimension of the n-dimensional asymptotic class, and the mu's can be real numbers, no reason to restrict them to rationals, and that there's a partition of the set of structures M together with parameters here, which satisfies two conditions. So the first one is that for each, so whenever for each I less than k in this partition, what you have is that the number of solutions in one of these structures M in your class C looks like mu I times the number of elements in the structure. Now it's di over n. roughly speaking. So what are the possible dimensions you have in an n-dimensional asymptotic class? The number of possible dimensions is going to be 1 over n, 2 over n, et cetera, up to n times capital N over n, which is just n itself. So you can have these fractional dimensions, and I'll say more about this in just one moment. But I want to stress again that for each of these di mu I pairs, there is a formula that tells you which parameters are the relevant parameters for the formula here, where you want to count the number of n tuples. So let me give you an example of this, of a three-dimensional asymptotic class, which I think gives you some insight into what's going on. So if you take a look, it turns out that the SL2FQ, the special linear group on FQ, consisting of 2 by 2 matrices over FQ that have determinant 1. This is a three-dimensional asymptotic class, and I'll say more about it in a moment. But if you want to count the number of elements in SL2FQ, it's an easy exercise that it's Q times Q squared minus 1. You can give this to undergraduates in an algebra course. So approximately Q cubed elements. So my M here, the 2 by 2 matrix over FQ, where you're varying Qs, is going to be roughly Q cubed. But you can define easily the diagonal matrices, so where you have A and A inverse on the diagonals, 2 by 2 matrices, so-called torus consisting of those, and you have just Q minus 1 of those, one for each non-zero element of the field. And so the size of that is Q minus 1. The size of the of the special linear group is Q cubed. And so when you take Q cubed and you divide by 3, you get Q. So that's why you need, for asymptotic classes like that, you can define sets that are fractional, of fractional dimension in the size of the structure itself. So that's a good example of why you get this more generality here. So the definition was due to Richard Elways, who was a PhD student of Dougal's way back in the last decade. One point that's important here is that how do you prove that a class of structures is a asymptotic class? So it turns out that there's a one variable criterion. So if the clauses 1 and 2 in the definition of an asymptotic class hold for every formula with just a single variable here, the number of parameters is free, then you in fact have an asymptotic class. And the argument for this is really what happens in, say, ominimality, where you have sort of a fibering or cell decomposition kind of argument. And in this case, looking at these finite structures, you sort of move your way up from the one variable case step by step to show that you get the result. You get it to be an asymptotic class for formulas in which the number of variables is arbitrary. So it really does help you in determining that. I should just go back a minute and just mention that if you exclude clause 2, you get what's called a weak asymptotic class. I won't talk very much about those at all, but I will say that for the one variable criterion, you really do need to bootstrap your way up using both the clause about the sizes of definable sets in one variable together with the definability of dimension and measure clause. So you bootstrap your way up each of those along the way. So what about examples of this? Well, clearly the class of finite fields is a one-dimensional asymptotic class. The class of all finite cyclic groups is also a one-dimensional asymptotic class, and these were early results. Now, here's an interesting one that I'll return to later. For each prime power Q congruent to 1 mod 4, let PQ be the Paley graph on the finite field FQ, which is the graph whose vertex set is the elements in the field, and you join two of them if their difference is to square. You don't have to worry about absolute, you don't have to worry about A mod, it's symmetric because Q is congruent to 1 mod 4. And so you just let CQ be the set of all Paley graphs, and this turns out to be a one-dimensional asymptotic class. So of course, the graph itself is definable in the field, but what's important is that you have to get out the definability of dimension and measure. And for this, you really need to use estimates that are due to Boyabash and Thomason. In they're certainly where we found is in the book on random graphs by Boyabash. So that's one example I'll return to a little later. And then a non-example, in case you're wondering about what can't happen, is a class of finite linearly ordered structures, because you just take the formula in the two parameters that says X is trapped between A and B, and that can have any size at all. There's no constraint on what the size of that set is. So no class of finite linearly ordered structures can be an asymptotic class. More examples. This one in model theory, it's for every smoothly approximable structure. It turns out Richard Elways was able to prove that there's a subcollection of finite approximating sets for the smoothly approximating structure that forms an asymptotic class. And these finite set witness the smooth approximability of M. I won't go into the definition of smooth approximability at this point. This is more for the model theorists. Then a beautiful result of Dugald student Mark Wrighton about the same time is that if you take a look at the collection of this collection of finite difference fields, where I've written them out in detail, you can read the slide, and these are where you have increasing powers of the Frobenius on the field, and as you move up, as you increase K. And it turns out that this also is a one-dimensional asymptotic class. And this relates to a lot of other work on ACFA for model theorists who know what that is. But the interesting consequence of this, I think, for people who are even not model theorists at all, is that via strong bi-interpretability results that Richard Elways proved, Mark can show then that every family of non-abelian finite simple groups of a fixed Lie type and rank is an asymptotic class. So when I referred just a little bit ago to the SL2 FQ, as you vary the fields FQ, and said this is an asymptotic class, this follows from Mark's result there. So it's a very nice big class of a big asymptotic class. There's also some other interesting stuff that goes on in asymptotic classes here. And so I thought I would mention a proposition, which is it's Tau's algebraic regularity lemma, which appears in a paper of his dealing with expanding polynomials over finite fields. And then Anand Pillai and Sergei Starchenko extracted the true model theoretic content of this. And then it applies not just to finite fields, but to arbitrary asymptotic classes. So let me distill what the statement of this is. So suppose you have an asymptotic class, and one of your finite structures in your asymptotic class that's sufficiently large, and you have a graph E on two subsets V and W. So this is a graph with all of the data VW and the graph relation definable. don't worry about the complexity issue here. Just let's think about having a definable graph on V cross W. So what then you can do is you can partition V into finitely many sets and W into finitely many sets, all of which are definable. That's the important point. And then to go down to 2, so if you let Dij here be the probability, the expected probability of the number of, so it's the probability of the number of edges in Vi cross Wj is the way to see it. So it's just the expected number of edges. And what the theorem states is pretty remarkable. It says if you take now any subset A of Vi and any subset B of Wj, then the number of edges between A and B is approximately the expected number of edges. So Dij times AB that you would get. So it's a definable regularity lemma on these sets, which is quite nice. That extends what goes on for if tau proved in the case of finite fields. Okay. Now, an interesting question that goes to infinite structures is, well, which structures or theories arise as ultraproducts of asymptotic classes? And the first obvious example is pseudo-finite fields, which is a field, an infinite field, which is a model of the theory of finite fields, easiest way to say that, which is just a set of all sentences true in all finite fields. It's pseudo-finite field. And what happens, so that's an ultraproduct of an asymptotic class. Now, an interesting one that comes back to the Paley graphs is that the theory of the random graph, which you can think of for those of you who are not used to thinking about this in non-model theorists, if you take a graph on the natural numbers and you flip a coin, a fair coin, say, to decide whether you're going to put an edge between two natural numbers m and n, then the almost sure theory of this is what's called the random graph, and it's an ultraproduct of the set of Paley graphs, of the class of Paley graphs. So, and that's a test case for Dougald and I wanted to find early on in talking about asymptotic classes. And it turns out that you actually do get a connection with infinite model theory here, which is every ultraproduct of an n-dimensional asymptotic class turns out to be super simple of rank at most n. So the rank in the model theoretic sense can collapse for what are clear reasons when you take the ultraproduct. But what it says is that when you take a look at the infinite analogs, the ultraproducts of an asymptotic class, that they live in a nice area model theoretically. So now, dimension and measure in asymptotic classes induces a dimension and measure on their ultraproducts by just looking at what the if you have a set in the ultraproduct, you can look at what the ultraproduct tells you that set's dimension and measure should be. So what we did then was we extracted a definition of what's called a measurable set, or MS measurable. And what this means is that there is a function h from the definable subsets of the structure M into n cross the positive reals, where you write h of x as the dimension of x and its measure, satisfying a few conditions. So the first one is that for finite sets, a definable finite set, the dimension h of that says 0 dimension, just cardinality of x. Then The next condition, 2, is really the asymptotic class condition, which says that for every formula, we're looking at a single structure now, M, an infinite structure. For every formula, there is a finite set of dimension measure pairs, so that the dimension and measure, so if you take parameters, coefficients, think of them, from A, and you take a look at the set of solutions, that the dimension measure of this should be one of your finitely many dimension measure pairs. And moreover, part B here is just saying that the set of parameters that pick out which of these finitely many dimension measure pairs you have is zero definable. So that's the condition there for that, the asymptotic class condition. And the third condition, which I've stated in its accurately, but really what it's saying is this: it's a fibering condition. So suppose you have a surjection from a set X to Y that's definable, it's in your structure M, and suppose that all the elements, all the fibers have, say, a particular dimension. Let's not think about all the different ones. So suppose that for every fiber, when you take F inverse of Y, that all of them look like d mu, the fibers. Now, then suppose that Y has dimension E nu. So let's not worry about breaking it up into the different finitely many sets here. So what the content of this is to say, what is the dimension measure of X? If you know the fiber is d mu, and if you know that the base is E nu, then the dimension of and measure of X, it should have dimension d plus E, and it should have measure mu times nu. So all of this is just more general in the case that you have finitely many different looking fibers in this case. So this is the, and people have called this the Fubini condition. I think it's better off talking about as a fibering condition. And this is what a MS measurable structure is. So all ultraproducts of asymptotic classes are going to be MS measurable. And we've seen that they have nice model theoretic properties. And the question is, what about measurable structures in general? Well, Richard Elways and Mark Wright and Dougal's students proved a while ago that if you have a measurable structure, then its theory is super simple of finite rank. So in fact, measurable structures in general are well behaved. Okay. Now, one quick note that's, again, easy for people to see is that C is not measurable, and particular no algebraically closed field of characteristic 0 can be an ultraproduct of an asymptotic class for this reason. And it's easy to check that the 2-to-1 surjection from X to X squared violates measurability. This is just quite clear because it's a 2-to-1 mapping, but the sets on the input and output are both just the field, the entire field. Okay. So I will say then, just to follow up a little bit on this, is coming back to model theory, is that every measurable stable theory is one-based. And a way to read this is that it's module-like and really not field-like. And this is a result of Anand Pillay and Charlotte Kessner. So that sort of gives you a sense of what the territory looks like for stable theories. And then I'll wrap up the conversation on asymptotic classes by asking some questions. First, is every measurable field pseudo-finite? And the missing piece of this is whether or not measurable fields satisfy are pseudo-algebraically closed. And this is based on, this is the one condition that's missing based on Axis theorem characterizing pseudo-finite fields. So this would be very nice to prove. This has been out there for at least 10, 15 years, and we just haven't been able to prove that nor see a counterexample. And then if it's true, it would lead to asking the question, is every measurable simple group a possibly twisted Chevrolet group over a pseudo-finite field? So building on what we know about the finite simple groups, that all of the, that we have that all of the finite simple groups of Lie type are asymptotic classes, is something like this true? And something even more far-reaching too is that if an asymptotic class is not one-based, is not module-like, so necessarily is going to be unstable, speaking to the model theorists, are arbitrarily large finite fields uniformly interpretable. And this would be a version of the Zilbert trichotomy. So these are some questions that have been around for a while, and that's all that I'm going to say about asymptotic classes. So now I want to move on to multidimensional asymptotic classes, and I want to motivate it with a theorem of Dario Garcia, Dugald, and myself. And where this comes from is, suppose L is a first order, is a language with a sort for vector spaces and a sort for fields, and it also contains a function for scalar multiplication. So this is different from the usual vector space structure where you have scalar unary functions for each of the elements of a fixed field. Here we want the field to vary as well as the vector space. So let's let C be the class of all L structures. That should be a script L, a typo I missed. VF, where V is a finite dimensional vector space over the finite field F. And now let, again, phi of x1 through xn, y1 through yn be a formula where the x's, as usual, are the variables whose solutions you're trying to count, and the y's are the parameters. And so the statement is that then there's a finite set. So given your arbitrary formula, there is a finite set of polynomials in the two variables v and f over the rationals, such that for every one of our vector spaces in our class C and all parameters, there is one of these finitely many parameters such that the size of the set of solutions, the n-tuples, that are solutions to the formula phi with the parameters b1 through bm, is roughly the size of the polynomial where you substitute in the number of elements in V and the number of elements in F. So this is something that's beyond asymptotic classes because you're no longer looking at just a monomial where you're concentrating on the size of the structure, but independently allowing these two sorts to vary. And moreover, for each polynomial in E, based again just on your formulas, there is a formula such that for sufficiently large of vector spaces here, and for all B1 through B parameters in M, then star holds if for those parameters, if and only if the defining formula there holds. So you have definability of this measure and dimension here in this context. So this is something that goes beyond asymptotic classes, and you can see then why we start thinking of multidimensional, although I think the confusion between n-dimensional and multidimensional is poor naming, but I've tried to change it, but been unsuccessful with my colleagues. So Now we get to multidimensional asymptotic classes, and this is work of Sylvia Anscombe, Dugald, myself, and Dugald's former student Daniel Wolf. Sylvie was a postdoc at Leeds when we started on this work, and the paper is most of the way completed. One of, I guess one should never make two of the authors heads of departments while you're trying to complete a paper, but I think we're getting closer to getting this done. So what's the point? So for a class of L structures and a tuple of variables, what we're going to do is we just partition them into as you just take a partition of this set. So the A's are going to be your parameters here. And we say that it's zero definable if for each element of the partition, there's a formula where you plug in the parameters, and that tells you when you're in that set in the partition. And then the definition is this now, and this is where you really go beyond asymptotic classes. So let R be any set of functions from this collection of finite structures into the non-negative reals. We'll say that a class of finite L structures is an R multidimensional asymptotic class, or an RMAC, if for every formula phi of x and x's and m y's, there is a zero definable finite partition of all structures with the parameter variables, and a finite set based one for each member of the partition of the parameter variables of functions in your set R of functions, such that the same condition holds, so that the number of solutions when you fix B is approximately h pi of m. And here the input is the structure M, not the universe of the structure, because as we saw in the previous example, what you're inputting into the formula there is going to be the size of your two sorts in the two-sorted vector space example. So this is a very general definition. We say that the functions are called the measuring functions of the formula phi of x, y, and when R is understood, we just call it a MAC, which I think we view as a bit of a joke calling it a MAC. But in any case, it's the same condition as before. Definability of your new dimension measure functions, your measuring functions, and the fact that you have finitely many of these for a fixed formula. We say that it's an R multidimensional exact class if in the above, instead of saying that the number of elements is approximately equal to h pi of m, that you get that they're exactly equal to them. So we'll encounter some exact classes as we go ahead. Okay, so let's see. Continuing examples, asymptotic classes. The vector space example that I mentioned as motivating the definition, and in fact, it's a polynomial MAC. So the functions are polynomials. If you take a look in the language of groups and look at the class of homocyclic groups, that is finitely many copies of Z mod P to the RZ, where P is a prime, then this actually is a mech. And this follows from work in the same paper of Dario, Dugald, and myself. The class of all finite abelian groups is also a mech. And this will be in the multidimensional asymptotic class paper. An interesting case is that if you have a pseudo-finite strongly minimal set, then there's a polynomial mech whose ultraproducts are elementarily equivalent to M. And this was generalized to by Alex von Abel, who is a PhD student at CUNY, who extended this to pseudo-finite uncountably categorical theories. And then Dugald's student, Ricardo Bello Aguirre, who has shown that the set of residue rings, Z mod NZ, where n is divisible by a fixed number less than or equal to d primes, all with exponent less than or equal to d, that this is a polynomial Mac when you expand by predicates for the individual subrings given by the factors, the prime factors in n. Otherwise, if you don't do the expansion, it's just a weak Mac. And then another example is if you fix a prime P and you look at the collection of all vector spaces with a non-degenerate, either you have to fix it to be either alternating or symmetric bilinear form, then this is also going to be a Mac. Then really digging into the work of Cherlin and Hrushevsky in their monograph on that the class of all finite envelopes of a smoothly approximable structure is a mech, and it turns out to be a polynomial mech. And this is extends what Richard Elways did, because he had to pick out, in order to get an asymptotic class, he had to pick out a specific set of finite envelopes. This says you can use all of them. And more generally, really working through the content in the Cherlin-Hrushevsky monograph, if you have a countable language, then the class of all finite L structures with at most D4 types is a polynomial mech. Then an example that Dugald likes very well is if you let M be a homogeneous graph, and then there is a mech with an ultraproduct elementarily equivalent to M if and only if M is stable. And there's a question out there whether this can be generalized to a homogeneous, to M being a homogeneous structure over a finite relational language, and the right to left implication actually does hold. The question is for the left to right direction. So continuing, as I mentioned for asymptotic classes, showing that a class is a multidimensional asymptotic class reduces to formulas in one free variable. So you let the parameter set be with any m variables, and you're just looking at solutions to formulas in one variable. But here you have to take a look take the ring generated by your set R of functions under the usual addition and multiplication for real valued functions. And then you can show that C is a bracket R Mac. So you just have to extend slightly the ring the class of formulas that you need in order to get a full Mac working from the one variable condition. Ultraproducts of Macs. So let's let C be the class of all finite that should be an L structure, not an M structure. VF as above, and let this be script M be a non-principal ultraproduct where both the field and the dimension of the vector space are infinite. Then M is super simple of rank omega. And it turns out that the reason why I mentioned this is because suppose that you have a polynomial ring over R in several variables, and that you have a class of finite structures that's an R Mac, then any ultraproduct of C turns out to be super simple, but now the ranks can get larger. So let's go back, hold on, yeah. And so let's see, right. So now let's take a look though at the class of finite of all, again, there's a mistake there, it should be L structures, of VF with beta, a non-degenerate alternating or symmetric bilinear form, and you take a non-principal ultraproduct with both f star and the dimension of v star infinite, then it turns out that this is not simple, in fact, and it's going to be, it's well known that this is going to be NSOP1. So the real question is, how tame can ultraproducts of R max be? I have about, let's see, okay, good. So I want to talk again, when you lift up these ultraproducts, we can then form a notion of a generalized measurable structure. So for this, start with a commutative ordered semiring. This is going to be what your measuring ring will be. You define an equivalence relation on elements of this as to whether they are in the same, call it Archimedean class. And then you take D to be the quotient of T under this equivalence relation. And you want to view D as your set of dimensions. So then we call D a measuring semiring if it satisfies the measuring condition that if you have X being less than Y in T, and the dimension of Y and the dimension of Z are the same, then when you add Z to both sides, X plus Z can't jump above Y plus Z. So this is something that, this is a measuring condition, but an easy way to see what this is about is in the case of MS measurability of an ultraproduct of a one-dimensional asymptotic class, you really have the ordered semiring R greater than 0, X to the N. So all mu X to the D, and you order this lexicographically first by dimension D and then by mu. And then you can easily check that this satisfies the conditions for a measuring semiring. So it's a ring, ordered semiring of monomials, just to give you a sense of what a measuring semiring looks like. So then you say that if you have a measuring semiring and M and L structure, then the structure is T measurable if there's a function satisfying the obvious conditions as before, that the measure of a finite set X is just its size, it's a finitely additive. This is the MAC condition here that says that you have finitely many, that you have the definability of dimension, the measured dimension definability, and that for any definable family that there are finitely many dimensions that work. And then this condition 4 is just the fibering condition that I mentioned before. So this is what generalized measurable structures look like. And it turns out that measurable, of course, implies generalized measurable. I gave you what the measuring ring is, basically for one-dimensional asymptotic class. All ultraproducts of max are generalized measurable. And again, you rely on the ultraproduct to determine the measuring ring, but here you have to do a little bit more work to get the measuring ring than you do in the case of, say, asymptotic classes. If you're generalized measurable, then you do not, looking to model theory, you do not have the strict order property. And it turns out that the generic triangle free graph is generalized measurable, and more generally, the generic KN free graph for all NR, and this is a result of Sylvie's. And so these are TP1 and TP2, have both the TP1 and TP2 theory. So it goes beyond, again, the simple context that we had before. And another question to ask, and this is where I will stop, is are generalized measurable fields pseudo-finite? And as I remarked before, this is not even known for MS measurable fields. And so with that, I'll stop. Thank you for your patience. And that's it. Any questions?
Okay, so are there any questions for Charlie? So one is anything known, say, about Frise limits or say limits where you have disjoint amalgamation? It seems.
Yeah, this is something, yeah, I didn't state it. It's more general than that what Sylvie does. And yes, this is true. You do get the results there. The same result. I just stated it in the case of the KN free graphs.
Other questions? Okay, so let's thank our speaker again. And also to remind you that in just about 5 minutes, there's this ASL networking experience. For that, you need to leave this Zoom room and go into the appropriate one, but hope to see many of you there. Thanks again.